We're going to continue on. We've been talking about last time. We got into really alcohols, like all day we alcoholed. So we did alcohols last time for a majority of it. Remember that alcohols have a functional group of OH. So that OH is the functional group for an alcohol. That OH group is a polar group there, and does give some alcohols some special sort of properties because we do have that sort of polar group where the oxygen is more negative, the hydrogen is more positive in there. So it does give alcohol some other types of functions different than, say, alkanes, alkenes, or alkynes. When we go to name alcohols, maybe not surprising enough, it is going to end with OL. So again, we basically take our alkane name there, kind of drop the E, and put OL. We also, when you got about 3 or more carbons there, we do need to give the location of the OH group. So it does take the priority when there's more than one place where you could do it. And obviously, if we looked at something like this or like this guy here, for example, do that, a little bit of that. Here we do have obviously 3 carbons, which is based off of propane. Here we do have the OH group, which tells us it's an alcohol. So drop the little boss part there. This is going to become propanol. And again, we do want to give the OH group a number. Again, about 3 or more carbons is where you have multiple options as to where that OH group could be. In this case, it's going to be really a carbon number 2, no matter which way you go. If it does make a difference, we always want to give the OH group there in the alcohol the lower number. So whichever way, we'll give it the lower number. So this would really be 2-propanol. Which again is the location where the OH group is at. This one particularly also, as we talked about, is that isopropyl alcohol, sometimes referred to as that's the CH3, CH3 group, basically through here. And again, sometimes common name, we have our CH3, our CH, and our CH3 group, which is that isopropyl group. Sometimes the people will name it that still. And again, that's rubbing alcohol. The reason we need to do the sort of label of the OH group is we could, in this situation, still have 3 carbons and has an OH, which means this would also be propanol. And in this case, though, the OH group there is at carbon number 1. So this would be 1-propanol. And again, because there's an option as to where that OH group could be located, really, as you probably have seen, organic nomenclature is all just about telling people where everything's located, basically. So we do have to kind of give the number. Obviously, again, here, we want to give the OH group the smaller number. We also want to, again, number which way that does that. Once we lock in the numbering that gives the OH group the smaller numbering, then all the other groups are just basically numbered accordingly in that order. If there is a situation where going in both directions, kind of like the first guy there, it doesn't really matter in terms of the OH, then the next important way that you would want to number is the groups that are attached, if there are any type of groups. We also talked about last time ways to classify alcohols, and alcohols can be classified as primary, secondary, or tertiary, just the way that we basically could classify carbons. And you can basically do it the same way as you classify carbons. So for example, again, if we look at this guy here, what we're really looking for when we want to classify a alcohol is we're still looking at the carbon, but it does need to be the carbon that's directly attached to the OH, or the OH is attached to that carbon, whichever way you want to look at it. So once we find that carbon where the OH is basically attached to it, we're going to count how many carbons are attached to that. And that's just 1, which means this would be a primary alcohol in this case. Actually up here, the one I drew first, right there, that is the carbon that is attached to the OH. It is directly attached to one carbon over there and two carbons over there. This would be a secondary alcohol in that particular case. And if we had something like, say, actually, we'll do that. So here, this is the carbon that's attached to the OH group. It's attached to 1, 2, and 3 carbons, and that would be a tertiary alcohol. So again, I personally like to count the carbons. Sometimes, again, people will count hydrogens rather than carbons, but again, the carbon gives you the exact number there. Now, we also talk about reactions that alcohols undergo and how we make alcohols, how we get rid of alcohols, and what happens to alcohols when they go through a redox reactions, basically. So we first actually talked about last time as well when we were talking about alkenes, that if you have an alkene that has a double bond and you add water to that, which is sometimes referred to as a hydration reaction. And remember, you can think of water as H and OH. Once again, here, the double bond will become a single bond in this addition reaction. And we will put on there basically our water as H and OH. And as we talked about last time, they do go to separate carbons, and H goes here, for example, and OH goes here. Again, we go from an alkene and we make an alcohol through this hydration reaction. In this case, it doesn't matter which way you put it because they have the same number of hydrogens, the carbons there that we started with. If they had different numbers of hydrogens in that double bond, remember the hydrogen ends up at the one with the most hydrogen to begin with. But here it wouldn't make a difference. By the way, we also talked about the idea of how to kind of get rid of an alcohol. So if you had something like ethanol here, and we heated it up, which is basically what that little symbol means, and maybe had a little bit of acid with it, we will actually remove the water that we put on, and we do remove it the same way we put it on. So OH from one, and we will need to take a hydrogen from an adjacent carbon, and that's going to remove as water. And then we will have everything the same, except for obviously those guys gone. And now remember, we do need to put the double bond back in. This is what is referred to as a dehydration reaction, right? When you basically remove the water. It's basically the opposite of making an alcohol. Obviously, in this case, we would go backwards from an alcohol to an alkene when we do remove the water in this case. We also talked about that if you have perhaps two carbons to choose from, where you would remove a hydrogen, you do want to remove it from the one that has the least number of hydrogens if there is a difference in the number of hydrogens those carbons have. If there's not a difference in the number of hydrogens those carbons have, then you can remove it from either one. You'll end up with the same thing. But if there happens to be a difference, then you do want to remove it from the one with the least. Kind of opposite how we put the hydrogen on to the one with the most. So if you're taking it off, we kind of take it off that way. Now we talked about our alcohols here that can uh, go through some reactions. And if we have, say, this guy here, and if we take this guy and put it through an oxidation reaction, which is sometimes referred to like that in equations, we see a little O in a kind of brackets, it means it's going to go through an oxidation reaction. Remember, the definition of oxidation that we're talking about here when we do alcohols, and by the way, again, this is our primary alcohol in this case. And the way that we do lose the hydrogen, again, is from different places. It is always from the oxygen, or OH there, basically. And it's also from the carbon that's attached from our to the OH group. Those guys will be removed and everything else will again remain exactly the same here. So nothing's going to change other than the highlighted guys we are going to get rid of in this case. And that's going to give us H2. As we talked about last time, when we do remove these hydrogens, we do need to also put in there a extra bond, and you will get a double bond between where the carbon and the oxygen is, where the two hydrogens basically came off. This is a aldehyde, which is an organic compound that you get here through this guy. And we also talked a little bit about this, and we'll see it a little bit later in another chapter. But if you continued to oxidize this aldehyde that you get as a result of this primary alcohol, you will actually get to go through an oxidation step, which is the other definition of oxidation, which is the addition of oxygen. So we're going to actually gain oxygen here on this part. The place, it is much more complicated than what I'm just going to say, but essentially what ends up happening is you just basically pop an oxygen right there and you get like an OH group there at the end. Everything else stays the same. So nothing really changes other than here you're going to put an oxygen in there and you'll get that OH there. And this makes another type of organic compound, which is known as a carboxylic acid. And that is the functional group there of a carboxylic acid. It's a carbon-oxygen double bond and the OH. Now, when you take a secondary alcohol, like we'll do this guy here, I think. Do our 2-propanol here. So our secondary alcohol. It also will go through an oxidation reaction. And again, it is basically that loss of hydrogen that we're talking about here. And again, from the oxygen and from the carbon that's attached to the oxygen is where the hydrogen is always going to be basically removed from. And once we remove that, again, nothing else changes in terms of the molecule, except for obviously we get rid of the two hydrogens we just highlighted there. We leave everything else basically the same. And we'll get the H2 that will come off. Again, here we do need to put in a bond there between the carbon and the oxygen, just like we do with the aldehyde. And this gives us what is known as a ketone. And that's, again, an organic group. And the organic group of a ketone is basically a 3-carbon run. And on the central part of that 3-carbon run, you have the carbon-oxygen double bond. So that's basically your functional group there. Again, that's different than our aldehyde. It's also different than our carboxylic acid in this particular case. Now, we also talked about what happens with our tertiary alcohol. So again, if we had a tertiary alcohol to start with, and you want to put it through an oxidation, you will get no reaction. And again, the reason you'll get no reaction is it does have this one hydrogen, but it is missing that second hydrogen that's sort of needed there on the carbon. It doesn't have a hydrogen directly attached to that carbon, and it will not allow it to basically go through an oxidation, so you will not get any product. Now, as we also talked about, pretty much for any oxidation reaction, if you go in the opposite direction, those are reduction reactions. So if we go in this direction, that's a reduction reaction. If we go in this direction, put the hydrogen back on, that's a reduction reaction. And if we were heading in this way, that's also a reduction reaction. So it's sort of the reverse of the oxidation reactions. Any questions on those reactions we talked about last time there? Now, we also talked about, again, the ability of an alcohol, because of the presence of this group here, to be actually pretty soluble in water. Again, as I said, about 5 or less carbons, and you're going to have some pretty good solubility of an alcohol and water. They're going to mix pretty well. And the reason they're able to do that is water is polar. And again, they're able to basically hydrogen bond with each other. The alcohol, whatever the alcohol may be here, it's able to hydrogen bond with each other. And that makes it really, really soluble. But again, as you build out all the carbons, more than 5, 6, 7, and above, what happens is you actually create too big of a molecule, and you have that molecule has a pretty big part that's non-polar, and it just gets in the way of it interacting well with something like water that's polar, and they really will not be soluble in each other as you go above that. On the other hand, as we also talked about, if you have some type of alcohol or compound that has multiple OH groups in it, that's going to increase the solubility in water, because everywhere there's an OH group, it allows it to interact well with water, and that would increase sort of its solubility. Alcohols also have pretty high melting points and boiling points, and that is because when we have alcohols, they again are able to hydrogen bond with each other. And again, that hydrogen bonding is a relatively strong intermolecular force, is probably the strongest intermolecular force you could have. And because of that, it takes a lot more energy to break those guys apart from each other. The result of that is you get a higher melting point and a higher boiling point for these guys than, say, something like, as we talked about, like an alkane that pretty much cannot hydrogen bond. We'll use dispersion forces, which are relatively weak type of forces, which means it doesn't take a lot of sort of energy, if you will, to get those guys to break apart. And that's again why things like methane, propane, butane, a lot of those sort of simple organic compounds, they're gases because they're held together by very weak interactions, and just very easily they could go into the gas phase, or are in the gas phase under normal conditions. And also why, again, some organic compounds that are liquids can very simply go from liquid phase to the gas phase and be very, what's referred to as being volatile, because they just kind of break apart, which is sitting there basically. They don't need a lot of convincing to sort of separate from each other. Any questions on any of that stuff we talked about there, I think, last time? Yeah. All right, then let us kind of continue on. I think we might have looked at some of this, but again, methanol is highly toxic. It's found in windshield wiper fluid, also paint strippers. It's absorbed and oxidized to formaldehyde and then to formic acid. And again, this is going to be oxidized, which is our removal of a hydrogen here and one of those hydrogens there, which gives us methanol, which is an aldehyde. And by the way, that's also known as formaldehyde as well. And it's oxidized here to our carboxylic acid, as we sort of talked about there a second ago. Ethanol, again, is sort of the alcohol of alcohols, if you will. And it's also sometimes referred to as ethyl alcohol. And again, here we do get our ethanol, and then we will get to our carboxylic acid, which is ethanoic acid. And in this case, you would get this here, which can break down into CO2 and water in a certain type of reaction that occurs. All right. So let's talk a little bit about some other organic groups. We'll talk about thiols here for a second. Thiols is an organic group that's actually a sulfur-containing group. Its functional group is SH. So it is similar to OH, but it is a sulfur-containing group. And if you've ever smelled sulfur, it does not smell so pleasant. And that's what they put into natural gas so you could smell it leaking just in case. And I'm imagining that's why we have a skunk here on the picture, I suppose, as we look at it here. They do have very not so great odors. They're found in cheese, onions, garlic, and oysters. And like I said before, they actually do put some sulfur into your natural gas so you could actually smell it. Otherwise, you wouldn't smell the gas, and that wouldn't be good if it would actually leak or something like that. So when we go about naming thiols, well, first off, we're not going to name thiols, so that's good. Good slide. I like it. So you do not have to name thiols. You do need to know the functional group of a thiol. And the other thing that you do need to know about a thiol is sort of the reaction that they undergo. So you won't have to name thiols, but again, you know the functional group. And if we have a thiol, say just a basic sort of thiol here, and we react it with another thiol here, these guys will basically react through an oxidation reaction. And what's going to happen here is the H's, one H from each, will basically come off. So one H from each of those guys will come off, and we'll get an H2 that comes out. And what happens is after you remove a hydrogen from each, basically they just squish together. The sulfur and sulfurs basically come together, and everything remains the same here. So you could just start on the left-hand side and just write what's there. So CH3, sulfur, then continue on, obviously leaving out the hydrogens, to a sulfur, to another CH3. This is what is sometimes referred to as a disulfide bond or bridge. So a disulfide bond or bridge is basically the two sulfurs coming together. You might probably also get the idea that, hey, if you go the other way, which is more like a reduction reaction. So if you started with the guy that has the disulfide bond and you added H2 to it, it is going to break apart right there where it comes together. So those guys are going to break apart. And again, you'll have basically this, and you will have this. And all you have to do is, since we have two hydrogens we want to pop in there, just give each one a hydrogen, basically, right? So we'll give this guy a hydrogen, we'll give this guy a hydrogen, and that is where those two hydrogens basically end back up. So if you take out the hydrogen between two thiols and put them together, you get a disulfide bond. There's an amino acid, cysteine, that has this group in it and makes a disulfide bond or bridge through amino acids when they get together. And again, if you want to break that apart, you just kind of put the hydrogen back in and they separate them. Best piece of advice would be, if you see it's two thiols and you need to take out the hydrogen, just line them up like I did there on the top one, kind of the SH on one and then the HS on the other. And then you can just put a box around the hydrogen, just draw the two sides together, and you'll have basically what's going on. Question on that reaction there. So why don't you try a couple here? Let's do this guy. Okay, so let's take a look. So again here, we're going to do the oxidation here to thiols. And again, what you see, you basically have two thiols. It's sometimes really helpful maybe just to take one of them there and just kind of turn it around and line it up the other way. And if we do that, we have something like HS. And I think it was just that, if I'm not mistaken. Now, when you do that, again, the oxidation in this case is two hydrogens. So all you have to do is just, again, box around the hydrogen. And that's going to give us, obviously, H2 here. And then when you kind of rearrange it and line it up like this, it makes sort of drawing the product relatively easy, because, frankly, you just need to copy everything other than the box. And the connection here is always the sulfur to the sulfur. So they always connect in together. And you'll end up with CH3, CH2, CH2S. And again, the connection here is sulfur to sulfur that makes that disulfide bond. And you just continue now on this side, and you got CH2 and CH3. Any questions on that one there? Now, the bottom one is really a reduction reaction. We're adding hydrogen, and then we already have the disulfide bond there, our bridge. So we know that when we put them together like we did in the first one, that is how they connect together from two separate things. So when we're going to break them back apart, that's exactly where we should break it apart, right there between the two S, how we put them together. Again, at this point, what I would start is just copy what's to the left there and what's to the right as two separate things. Once again, nothing else is going to change, so I'll just do it down here. So we're just going to copy pretty much identical to what's there. I count it right there. And we have it, obviously. And then here we can draw this guy as a separate thing, an S and a CH3. At this point, what's left to do is basically put our two hydrogens in, one to each of these guys to get them back to a thiol. So pop a hydrogen there, pop a hydrogen there, and there it is. Yeah. Any questions? You know, like I said, the functional group, what it makes two reactions, how to draw the products like that. Any questions? We will not do any naming of files. Now we have any questions?
Now,
Yeah.
rewrote it.
Yeah. Yeah. So if you're asking, originally I had it like this, I think, right? It was written like this, right? And sometimes if you could recognize that again, these are both thiols, and that's really where the connection turn it around and kind of line up the sulfurs together. That way you could kind of box it up. And because the connection when two thiols get together is always between those two sulfurs. So you're not maybe what some people will do is, you know, because it's kind of written that way, then they know they're doing some type of weird connection like that and trying to put them together, and you'll get the wrong thing. So again, that's why it's important to remember how the connection happens. And sometimes it's just easier to turn them around and line them up, like box around the hydrogens. And at that point, it's just copying what's there basically each side of the box and just put them together through the sulfurs. Yeah, technically you could write H2 like I did there. That's basically what's being removed. So it's kind of similar to what we've done before, where we kind of removed the two hydrogens and then we put a bond in. In this case, we're removing a hydrogen from each, which is two hydrogens, and we're inserting a bond. So the two hydrogens to come off ended up right here, for example, and right where I just circled. I just ran out of room, so I did this plus this. But yeah, so but you can write the hydrogen. Yeah, yeah. So right there, yeah. So the main thing obviously the disulfide bond, but you do get the H2 that comes off with that. Yeah. Other questions? Yep.
S and H.
Yeah.
Why have like the hydrogen like in the middle of one and out?
It's just the way I drew it. You talking about here? You here in those two places? You mean? Is that what you're talking about, or are you talking about the original one or this guy? The original one, yeah. So you could you don't have to necessarily. It's kind of the same idea as like with an alcohol. Again, you can write it just like that with no hyphen between the S and the H. And that's similar to how you could kind of write the alcohol group like as OH, or you could write the alcohol group O-H. It's not wrong to do that. Here, I might have put the dash here just again to show that that hydrogen is the one that's going to be removed. So you don't necessarily, you could put the dash there or you don't have to. Either way, it's okay in that case. Yeah. Yeah. Other questions? Okay. All right, oh, that was quick. The next organic group that we're going to talk about is an ether, or ethers. And ethers have a functional group. Basically this run, it's basically a carbon, oxygen, carbon. So that is sort of or to be able to, like, as an ether. And as you can see on the bottom there, we have CH3OCH3, which again, if you kind of drew everything out, looks like this, looks like this. And by the way, again, the oxygen in the middle, although it is usually never drawn in this organicness, still has those kind of non-bonding electrons like, water has and stuff like that. But for simplicity, a lot of times it's not drawn or anything like that. So what you can see here again is the functional group of that ether, and that's the carbon, oxygen, carbon. So that's what you're looking for, are here carbon, oxygen, carbon. It's basically the functional group there of an ether. Now, ethers have a bent or V-shaped geometry like water because, again, when you actually take into account the non-bonding electrons that are there, 1, 2, 3, 4 electron pairs and 2 bonds, which is just like water. It is that bent or V shape. That's that left angle that happened. Now, when we draw it, say, in line structure, it looks something like this, perhaps. Yeah, and of nature would be it. And again, the oxygen in the middle is just the oxygen there. And then obviously at the ends here, we have a carbon that has 3 hydrogens, right? And we have a carbon that would have 3 hydrogens as well. So again, for simplicity in line structure, that I just drew up there, and that's on the bottom there, that's essentially what it would look like, right? Now, there's a couple of different ways to name ethers, but it looks like your book goes with the common way of naming, so we'll go with that. And when we do sort of the common naming of ethers, pretty much you just want to do it very simply. You just want to go to the oxygen that's in the middle, right? And you want to go to the left and the right of the oxygen and see what groups you have going on. So that's a 1 carbon group, which is a methyl group. That's a 1 carbon group, which is a methyl group. And that's 2 methyl groups in the same compound. So that is a dimethyl. And then you just simply put ether at the end. So that's the common way of naming, which is diethyl ether. The IUPAC way of naming, which we will not go with, but just to show you sort of how that works, we put kind of oxy in front of the group. So this would be methoxymethane. And we'd use the other group as the longest carbon chain. So we put like methoxymethane. Dimethyl ether seems a lot easier, so we'll go with that one there. So again, oxygen group to the right, group to the left, and just basically put ether at the end of it. And here we could take a look at another one. We got CH3, OCH2, CH2, CH3. Here again, we would focus on the oxygen and basically identify the 2 groups that are present. So to the right, we have a 3 carbon group, and to the left there, we have a 1 carbon group. And that's going to give us obviously a methyl group here, and that is a propyl group. So just like anything else in terms of groups, we do go alphabetical. So we would go with methyl, propyl, and then again, just put ether at the end of it. Again, the group's basically named. To show you again, the IUPAC way of naming, we would go with the one that's the longer carbon as the base of the name, which would be propane. And we would put that oxy onto that one. So this would be methoxypropane is the IUPAC way of naming. But again, we're going to roll with this guy here. Questions on that there? So let's take a look at a couple here. Maybe we'll do it here. So why don't you name this guy? Why don't you name that guy, and then why don't you draw, let's do something. Let's do ethyl pentyl ether. All right. Sigma ether, and if you're not sure, that is a carbon. Obviously, that is an oxygen, and that is a carbon. So that's your carbon, oxygen, carbon run that makes it an ether. So since we're going to go with the common way of naming ethers, you can pretty much, if it helps, put a circle or a box around the oxygen. And then basically all we want to do is look to the left, look to the right, and kind of identify how many carbon groups we got going on. So I'll go here to the left, and again, I'll start here. That's 1, 2, 3, and 4. So a 4 carbon group is a butyl group, right? And going the other way, we actually just have 1 carbon there at the end, right? So that's going to be a methyl group. So we're going to go alphabetical here. So that's going to be butyl methyl. And again, we're just going to put ether at the end of it for common name. Any questions on that one there? Going. It does. So this is so we're using the common way of naming ethers, and the common way that you name ethers is to put ether at the end. Again, the IUPAC way is a little bit more complicated with that oxy and then the longer chain. So we'll just go with the common way, and that will have just ether at the end. Yeah. Other questions? It's kind of like similar to the common way that sometimes alcohols are named, like isopropyl, and then you just put alcohol at the end and stuff like that. Yeah. So here again, we see our ether, carbon, oxygen, carbon. So that tells us it's a ether here. Once again, I'm just going to box up the oxygen and just count up what I got going on. I got a 2 carbon group there. That's an ethyl group. I got a 1, 2, 3 carbon group here, which is a propyl group. And at that point, alphabetical is in alphabetical order there. So ethyl, propyl, and again, just going to put ether at the end. Now we're going to draw, and when we draw it, we're going to do what we normally do, which is work backwards in the name, right? So ether tells us that it's got to have as the functional group, right? Carbon, oxygen, carbon. And actually, in this case, since we have the common name for an ether, that is actually what I'm going to start with. I'm actually going to start with like the ether group. And I know the ether group is basically a carbon, oxygen, carbon, right? That's basically the ether part of it. Now I need to add my group of the oxygen, right? And again, since you're drawing it, you can put the groups on either side, whatever way you want to do it. A pentyl group should have how many carbons? Should have 5, right? Now, the way I did this, though, I've already put a carbon on each side, so I got to make sure I count that one. So I don't want to add 5 more, which would give me 6. I just want to start with, say, 1, 2, 3, 4. Maybe I should have done the other guy on that side. It would have been better, probably. We'll just get rid of that part there. All right. So, all right. So we have ethyl. And we'll go 5. So again, because I already put that carbon, I want to make sure I don't add too many there when I do that. That takes care of the pentyl. The ethyl is going to go on the other side. Again, I've already put a carbon there, so I just need to actually add 1 more to get me to a grand total of 2. Now, much like we do with everything else, is going to be hydrogen at this point. again, to give carbon 4 bonds. So we'll need 3 hydrogens there, 2 there, 2 there. We'll need 2 there, as it got a little tight. We will need 2 there, and 2 there, and 3 there. Yeah, and there you go. Yeah. So kind of the same thing here, but since it is sort of an ether, I'm gonna actually start with the middle part because kind of work my way out since I want to put what's on the left and the right on as groups. Any questions on that? If you're going to do a little line structure, you'd still kind of do the same, to be honest with you. You could start with the oxygen and just draw a couple lines down. And again, that's basically 1 carbon on each side. And on the right there, we had 5. So 1, 2, 3, 4, and 5. And on the left, we had 2, which would look something like that, right? If we're just going to draw sort of our line structure. Any questions on ethers or how to name or draw them? Yeah. I'm adding the H's down here. Yeah, so those are carbons, so they need to get to 4 bonds. So just like we do with everything else, I kind of want to start with the carbons and then add enough hydrogens to give each of those carbons 4 bonds. So that's why the carbons at the end needed 3 because they only had 1 line coming in and kind of the lines coming in. So in that case, other questions? Before I decorated this page, ethers are used in anesthesia, right? Puts you to sleep, right? The ethers, take a long little sleep there. And traditional ethers were used as anesthesia, but there was some sort of side effect. The hydrogens. So over the years, they replaced some of the hydrogens on there, on the sort of ether with some halogens like fluorine. Also makes it a little less flammable, which is probably good since you're using that in a situation where probably the patient's sleeping. You don't want anybody to catch on fire, and they're not as volatile as well, so they won't hopefully catch on fire and stuff like that. So over the years, again, we still have the basic sort of ether structure on these guys here. You can see carbon, oxygen, carbon, carbon, oxygen, carbon. But again, they sort of replaced some of those hydrogens there with some fluorines along the way. All right, so let's draw some here. Draw these guys. Why don't you also draw? Let's do let's do 3-methyl 2-hexanol. And let's do actually let's do methyl octyl ethers on all this. So I see pentanol. OL tells me it's an alcohol, right? So gonna start with just our 5 carbons. 1, 2, 3, 4, and 5. 3-pentanol tells me on carbon number 3 is where my OH group is located. And again, since you're drawing, you could put it either way, which actually I think will end up at the same one, regardless of which way you go. I'm going to put it right there, carbon number 3. Now we're just going to fill in our hydrogens to get carbon to 4. So we need 3 there, 2 there, just 1 there. We'll need 2 there and 3 there. Yeah. Questions on that one there? All right, so ethanol, again, OL tells us alcohol, ethanol tells us it's just 2. This case doesn't matter which one you put it on, so we'll put an OH there. And again, we'll just put our hydrogens in. So I need 2 there and I need 3 there. Yeah. That would obviously be more of a condensed structure, yeah. Question on that one there. Diethyl ether. So ether tells me I have this connection, carbon, oxygen, carbon. And diethyl means I have an ethyl group on either side, and an ethyl group is 2 carbons. Once again, I got to remember I already put a carbon, so I just need one more there, and I would need just one more there. Now we're going to put our hydrogens in. We're going to go 3 hydrogens, 2 hydrogens, 2 hydrogens, and 3 hydrogens. Any questions on that one there? Yeah. I'm not sure. No, they're both ethyl groups, so they're both 2 carbons on each side, if that's what you're asking. Yeah, so they're both, and that's why it's diethyl, so there's just 2 ethyl groups, so they're both the same. So because they're both the same, obviously it doesn't matter which way you go. Yeah. And by the way, if they were different, it wouldn't matter which side you put either one on, as long as they went on obviously opposite sides. Other questions? All right, so hexanol here again tells us it's an alcohol. We can go with 6 on this one. 1, 3, 4, 5, and 6. 2-hexanol tells me it's that carbon number 2. So I'm going to go left to right, which means that's going to be my carbon number 2. And that means that carbon number 3 right next door, I should have a methyl group, right? And now we're just going to fill in our hydrogens. So I need 3 there. I need 2 there. I need 2 there. I need 1 there. Need 1 there. And I need 3 there. Yeah. Obviously, like we've talked about previously, if you wanted to call carbon number 1 on the right-hand side 1, then you could go in the other way. It's basically the same thing, just turned around. Yeah. Lastly here, my regrettable one. We're gonna go. I'm gonna go this way. I think I'm gonna go carbon, oxygen, carbon because that's an ether, and I have an octal which is 8. So I'm gonna actually go to the left here because I have no room to go to the right. So that is 2, 3, 4, 5, 6, 7, and 8. And I left me a 1 on the right there, so that's good for my methyl group at that point. Again, here we'll put in our hydrogen, so I need 3. I need 2, 2, 2 all the way through here. And obviously at the end here, I will need 3 of them. Yeah. Obviously, you could have done it the other way. It's just the same thing, just flipped around. Any questions on any of these here? Ethers, thiols, alcohols, drawing, naming, except for thiols, or in those reactions. Okay, so we're gonna continue on here, and as we talked about earlier, again, the solubility of alcohols, it has to do with that OH group and the ability to hydrogen bond. And as I was mentioning earlier, again, in terms of solubility, kind of low number carbons typically will be soluble when they're alcohols. But as you can see here, once you just build out that sort of non-polar part of the alcohol, it just again gets a little bit too big, and there's too big of a non-polar part to allow the water to really interact well with it. Again, sometimes referred to as steric hindrance. It just kind of gets in the way. And again, for something to really be soluble in water, you need to replace water and water interactions with similar type of interactions, things that are not as super bigger than water or anything like that. And that's what we see in this table here. You can see upwards of 3 carbons, you're pretty good. When you start hitting 4 carbons, you're running into a little of it not being soluble in that nonpolar part. And definitely by about 5 or more carbons, even though you still have that OH group for it being an alcohol, you're going to see pretty much no solubility in water. Again, because it just gets too big, that nonpolar part where all the carbons and hydrogens are, which would be this part of it here. It just gets too big and in the way and doesn't allow it to interact well with water. But relatively smaller ones, definitely these first 3 or so, are not too big to interact well with water, especially something like methanol and ethanol are pretty soluble in water. That means if you took some methanol and you mix it with water, it pretty much will all just look the same. There will be no layers or anything like that. If you pop something like that that's insoluble in water, you would start to see some layering happening as they wouldn't mix together. And again, that's because they're not going to be soluble and mixed. All right, phenols, as we talked about as well, which are our benzene rings that have the OH group and are alcohols. They can react with water to produce some substances that are used as antiseptic, and they do an acid-base sort of reaction, sort of the Bronsted-Lowry definition. But the sort of acidic type of solution. All right, so we take a look at these two here. Which one should be soluble in water and which one will not be soluble, perhaps? Would the first one be soluble in water? It would not. And even though it has this polar group, that's a lot of carbons, basically, right? So we got this non-polar part. We have this polar part, so to be insoluble, right? In this guy here will be it will be soluble in water again, although it does have some carbons here. It's relatively small. It's less than definitely 3 carbons here. And we have that OH group, so this guy should be soluble in water. All right, so continuing on with our journey through organic molecules, we're off to 2 organic molecules that we actually saw when we talked about the oxidation of alcohols. So these are the 2 products that you get when you oxidize a primary alcohol and also a secondary alcohol. Aldehydes. So that is the functional group of an aldehyde. A ketones functional group is you need basically 3 carbons in a row. And on that middle carbon, you need a double bond. And the carbon-oxygen double bond here, this is what is referred to as a carbonyl group. And specifically, this guy is what is sometimes referred to as a carbonyl carbon. It is, by the way, a polar group. When you look at electronegativity difference, the oxygen is more negative, the carbon is more positive. So difference in basic electronegativity, but it is a polar group that you actually have here in this particular case. The simplest ketone is acetone, which is also known as propanone or dimethyl ketone. And it's a colorless liquid that's used to remove nail polishes and a lot of solvents and stuff like that. As I mentioned before, we do get a aldehyde from the oxidation of a primary alcohol. So if you take a primary alcohol, as we talked about, and you oxidize it, you will get your aldehyde. Just like if you took a secondary alcohol, like we talked about, and you oxidize it, you will get your ketone. So again, we saw basically the formation of each of these earlier in this lecture when we were talking about the oxidation and reduction there, or really the oxidation of these types of alcohol. As I mentioned before, this aldehyde and ketone both have carbonyl groups, which again is a polar group, and does give aldehydes and ketones some properties. Allows it to interact in certain cases with water and stuff like that because it has that group attached. By the way, when we talk about aldehydes or ketones, there is sort of a difference where those functional groups end up. So what I mean by that is this aldehyde, the functional group for an aldehyde will always be at the end of the molecule, one end or the other. And the reason it will always be at the end is it has a hydrogen at the end. And hydrogens can have how many electrons? Hydrogens can only have 2 electrons. and it's going to always have one because it has a bond, right? So that hydrogen at the end, it actually has to put that whole functional group at the end. It can never be stuck in the middle, otherwise hydrogen will obviously too many bonds. On the opposite end of that, the ketone, because you need a 3-carbon run always for it to be a ketone, the carbonyl carbon can never be at the end because it's got to be one in from the end to have basically 3 carbons in a row. So you'll never have, again, that carbonyl carbon at the end for a ketone. Now, when we look at aldehydes and ketones, again, the groups and line structure, we would draw it like this for an aldehyde, and you would need to put the hydrogen at the end here, because if you did not put the hydrogen at the end, it would imply that that is a carbon, right? So you do have to put there if you're drawing sort of an aldehyde and line structure. On that same note, you would not put obviously a hydrogen there at either end of those guys if you're drawing a ketone, because you need the 3 carbons in a row, and that would get you your carbon, carbon, and carbon basically happening there. Obviously, you could have more parts to it than just those 3 carbons, but that's the functional part of it. Now, sometimes an aldehyde group written in sort of condensed formula like that. So if you see like a CHO, that's basically telling you that is the aldehyde functional group. So sometimes that's how it's sort of abbreviated in problems and stuff like that. Also, CO is usually the carbonyl group there, that carbon oxygen double bond is sometimes abbreviated like that. I would say probably most of the time it's just better just to draw it out so you don't get confused maybe as to what you're drawing and stuff like that. Just draw out the group. So let's talk about naming aldehydes. And when we name aldehydes, we will go with the IUPAC way of naming. And frankly, it's an AL, not to be confused with OL, which is for alcohols. So here with our aldehydes, we basically just simply count up carbons. That is 1 carbon, which is based off of methane. We'll drop the E, and this will be metha, end of it there. By the way, that is also known as formaldehyde, yes. Methanol and formaldehyde are the same thing. A little bit sometimes. So formaldehyde is used along the way. If we have carbons here, so 1 and 2 carbons based off of ethane, drop the E, this is ethanol. Now, with actual out, I need to give the location of where the carbon oxygen, and that is because it's got to be at the end. So it's either one end or the other. So you don't have to, like we get double bonds, triple bonds, or OH. You have to give the location when you see the carbon oxygen double bond, because it should always be at the end. With that being said, if you have something else attached, say we had something like this, perhaps. We would still want to find the longest carbon chain that contains the functional group here. So if we go straight across 1, 2, 3, 4 carbons, by the way, you could also go down and to the right as well and get 4 carbons. So that either way you want to go is good. But 4 carbons seems to be the main part here. And that would mean that what we have attached is a group, which is our 1 carbon group right there, right? So we'll start 4 carbons, and 4 carbons is based off of butane. It will become butanal, Al. Numbering the groups, each we do a number in aldehydes, it is still really the priority in terms of numbering. So where that carbon, oxygen, the hydrogen, that carbon should always be carbon number one. So wherever that guy is located for naming other groups that may be attached, that should always be carbon number one, which means that carbon number three is where our methyl group is at. So that will be 3-methyl butanal, Al here. Any questions on that there? Yeah. Yeah, so these names down the bottom. Yeah, so these names down the bottom are names that are usually used. I would say out of all those common names, we'll just go with the first one that you should be recognized, which is formaldehyde, which is methanol. The other ones, truthfully, people do, but very much in here. But just in case, that's sort of what they are. But this one, again, you should be familiar with what it is. But we'll go with the IUPAC way of naming, which is what we just did there towards the top. Yeah. Other questions? So as you can see here, we got methanol, ethanol, propanol, which has 1, 2, 3 carbons, 1, 2, 3, 4. We do not get it's located, but it would be carbon number one for anybody else in terms of numbering. Where give the name for that one. Why don't you also tell me what I just drew here? I'm not really sure what I'm drawing, but maybe I'll do not that. Let me come back here, get rid of that. We'll do that and that. And why don't you also draw, let's go with 2 bromo. Here we're counting along. We do need to make sure we include the functional group. So we got 1, 2, 3, 4, 5, 6 in that case. We could also, I think, get 6 if you started 6 here. That would be 1, 2, 3. Again, it could the straight way is sometimes easier to see everything else that's attached. So we'll just make that all green. So we'll just go this kind of main way here. 6 carbons. Remember, the guy at the end there is a hydrogen, not a carbon, so you don't want to count it. So 6 carbons, which with obviously our functional group here, basically right there, is going to be based off of hexane, and that's going to then have an Al at the end of it. That's going to be a hexanal. Remember, again, here we don't need to put the number where the carbon-oxygen double bond is located, but that will be carbon number 2 is here, carbon number 3, carbon number 4, carbon number 5, and carbon number 6, if we go that way. We can then clearly see at carbon number 4 there, we have a chloral group and a carbon, a methyl. So again, we're going to go alphabetical here and put it together. So that will give us something like a 4-chloral, 5-methyl, and we'll lay up a little hexanal at the end of it. Yeah. Any questions on that name there? Looking at there, I think we just go straight across and we will have the most. 1, 2, 3, 4, and 5 look like the most. Your other option would be up and to the right, which is only 3. So that's obviously less than what we need. Again, you should recognize the functional group here. That's a carbon oxygen double bond and a hydrogen. So that's our aldehyde group right there. So that means I forgot how many carbons, 5, I think it is. So that's going to give us a base of the name here of pentanal, Al. Once again, this is going to be carbon number 1, where carbon oxygen double bonds located. That would make that carbon 2, carbon 3, carbon 4, and carbon 5. And we can see here, carbon number 2, we have a methyl group. So a 2 methyl pentanal. Any questions on those there? Yeah. Are you talking at the very end here? Are you talking right here? Was that? Uh, oh, this H right here? Is that there? You don't have to name it. It's just drawn out as an H. It's attached to the carbon, so it's not a group. So remember, hydrogens are really not groups. The only time we kind of think of them is when we did like you kind of think of groups, but they're really not named. They're just the hydrogen there to give carbon enough bonds, basically. Yeah. Other questions? Exactly, yeah. So again, I'm not sure why they kind of drew it out. Maybe they drew it out because there was the methyl group on the other side, but that would be the same if they just wrote it like the CH3, CH2, CH2, and then CH with the methyl group coming down, and then obviously our carbon oxygen kind of bond, stuff like that. Yeah. Other questions on that? Okay, so we're gonna draw here. So that's butanal. The Al tells us it's right, and the butane part tells us that it is 4 carbons. So just like normal, we're gonna kind of go this way, and I'm gonna start with the 4 carbons. But here I am going to put the aldehyde group. And again, since you're drawing it, you can put it on the left there if you want. You can put it on the right carbon, but it does, right, has to go on the end carbon, right? So we do have to put it at one of the ends. I'll go to the right here and put it. And remember, that's a hydrogen there at the end, right? That makes it the aldehyde group. Because I put my aldehyde group there on the right, that would make this for me carbon number 1. Obviously, if you put it on that 2, there is a bromine, right? That's what the 2-bromo basically means. At this point, we're going to fill it up with hydrogens, the carbons. So we would need 1 there. We would need 2 there, and we would need 3 there. And again, if you're going to do maybe like a line structure, you would still kind of do the same thing. You could start with 1, 2, 3, 4 carbons. And at this point, what you could do is you can double bond your oxygen and put your aldehyde group on there. That again, because I put a hydrogen at the end, would still leave me only 1, 2, 3, and 4 carbons, right? So we're still good. And then obviously you wouldn't normally put the C's, but then we would put our BR there. Yeah, so you could do it that way as well. Any questions on that there? Yeah.
So when you drew out like the CH2,
Huh?
the bromo,
Mhm.
at the end you did C hyphen H. So if we just put CH, would that be wrong?
It technically it's okay. Yeah. I will say most of the time people kind of draw out the group even in the condensed formula, but kind of like what they did here. I'm assuming that's what you're asking. If you kind of did like that, that's perfectly fine as well. Yeah. Other questions? Okay. All right. Now that we did aldehydes, let's do ketones. So when naming ketones, we drop the E off the alkane and we put ONE. So that's kind of like our ketone group there, ONE. And we do have some common names for ketones, but the way that we do common names is similar to how we do it with ethers, but for us, we are going to do the IUPAC way of naming. And the IUPAC way of naming is, like I said, we'll put the ONE at the end of the alkane name. We do, unlike aldehydes, because the carbon-oxygen double bond is never going to be at the end, we do at some point have to give the location of where it's at. And for ketones, that usually is about 5 or more carbons. So when you get 5 or more carbons, you do have to kind of give the location of where the carbon oxygen double bond is, just like we did with double bonds, triple bonds, the OH groups. So here with this guy, it starts about 5 or more. The reason it starts at 5 or more is because that's the point where you could have it at different locations, basically. So if you have 4 or less, you really don't have to give the number of where the carbon oxygen double bond is, because it can only be in one case. Now, also because you has to have carbon run for a ketone, you got to have that 3 carbon run with the double bonded oxygen there in the middle. The simplest ketone you could have has to have 3 carbons. You can't have anything less than that because you won't have 3 carbons in a row, right? So that is the simplest ketone that you could have. And we would name it the same way. That is 3 carbons, which is based off of propane. We drop the E, and this is what is known as propanone, O-N-E, like a ketone. Yeah. There could only be one place where that double bond is located, right? It's, no matter which way you go, it's got to end up in the middle carbon, basically, right? So you don't need the number. If you get to 4 carbons, you could put the double bonded oxygen there on the middle one here. And this would be 4 carbons, which is based off of butane, and this would be butanone. Now, you may be saying, when did I get something different if I put my double bond there? So if I put my double bond there on that carbon and put in my hydrogens, if we just counted the carbon, where the carbon oxygen double bond is, and again, we want to give it the smallest number. If I did the guy on the left here, that would be carbon 1 and 2, right? Now, if I did the same thing for this guy, where would that carbon oxygen double bond be? Carbon number 2. So even though it may look like there's different locations where it's at, you would actually name it the same way because the carbon oxygen double bond's at carbon number 2. So again, it's not until you get to 5 or more carbons with the ketone that you do need to put the number where that carbon oxygen double bond is located, as you do that. So here we also have this guy here. And this is cyclohexane it's based off of. This is a ketone group here, 1 carbon, 2 carbons, 3 carbons, double bond on top. This becomes cyclohexanone. And if you put a methyl group there, for numbering purposes, although we do not need to give the number where it's located, that is going to be carbon number 1. And that means that we will want to give this guy the smallest number, which is 3. Obviously, if you went counterclockwise, it would have a larger number if you went the other direction. And that's how we get to 3-methyl cyclohexanone. So in sort of a ring type structure that's a ketone, you don't need to give the location of the carbon oxygen double bond, but it is assumed to be carbon number 1 if he has to use it to number anybody else's there. It's always sort of the priority in terms of numbering. First off, any questions on that there? What is the common way that we name ketones? If you're going to roll with a ketone commonly, you go right there where the carbon oxygen groups. That's a methyl group. That's a methyl group. This is also known sometimes as dimethyl ketone. Yeah, kind of like what we did with the ethers. You go to the left. If If you went over here, that's a methyl group. That's an ethyl group, alphabetical. That would be ethyl, methyl, ketone. Yeah. So that is the common way that you would name ketones. We will go with the IUPAC way of naming, the ONE way, but sometimes people will use the common name. So that's what you see down here, kind of in parentheses, are the common names of it. Any questions on up there? All right, so why don't you name this one? Why don't you also name why don't you name that? Why don't you name that one? Name that one, and why don't you draw? Let's go with actually. Let's go with 3-bromyl 4-methyl 2-hexanone. That's a. So we'll start with the top one, and we'll just count some carbons here. Got 1, 2, 3, 4, 5, 6, and 7. I think you'll also get 7 if you kind of detoured up that way as well. And again, you can. It doesn't really matter whichever way you want to go. So I'm gonna go with the 7 I just counted there, and again, that does include the carbon-oxygen double bond. So 7 is going to be based off of heptane, and this is going to be heptanone, O-N-E. Again, I do know this is a ketone because I see really my carbon, carbon, carbon run, right? With the double bond there in the middle. So again, that is basically what you need there for it to be a ketone. In this case, that part right there, basically here, all that, right? All right, so now that I did that, I do need to give the location of where that carbon-oxygen double bond is located because there's more than one place and it's more than 5 carbons. So if I number left to right here, that'll be 1, 2, 3, 4, 5, 6, and 7. If I number right to left, that would be 1, 2, 3, 4, 5, 6, and 7. In this particular case, does it matter which way I go for the carbon-oxygen double bond? No, they both end up at carbon number 4 in this case, right? So it doesn't make a difference for the functional group, right? So the next important thing then would be the group that's attached there, right? And we do have a group attached, which is this little methyl group hanging out right there. We would then want to kind of switch our priority to whichever way would then give the group the smaller number. And in this case, we would want to go in this direction here, as that would give the group. Again, for the carbonyl carbon, where the double bond's located, it doesn't really matter which way you go. It's kind of a tie. So the next important thing after that would be the group. So we want to give that group then a smaller number if we can. We do need to put the 4 here. And the 4, though, is for where the carbonyl group is located, the carbon-oxygen double bond. And now we could put our 2-methyl in there for heptanone. Any questions on that one there? All right, so we'll go left. Why not? We got a little ring action happening here. So 1, 2, 3, 4, and 5 carbons. So that is 5 carbons. That would give us cyclopentane. And this then would become cyclopentanone, right? ONE, because again, it is a ketone, and the ketone is right here. Carbon, carbon, carbon. Again, 3 carbons in a row with that double bonded oxygen there to the center carbon, right? Now, again, here, this is sort of a ring structure, so we do not need to give the location where the carbon-oxygen double bond is. But in this case, we do have another group attached, and where the carbon-oxygen double bond's located is going to be carbon number 1. And again, we will now want to give that group the smaller number. So if we just go to the right there, that's going to be carbon number 2. And that would give us something like 2-chloral cyclopentanone in that particular case. Questions on that one there? All right, so we'll go to the guy on the right here. And again, I think if you go straight, you got 1, 2, 3, 4, 5 carbons. Once again, you could also go up 2, 3, 4, 5 as well, whichever way you want to go. I'm just going to take the kind of straight chain there, and that means that I do have one group attached, which is my methyl group hanging out right there. 5 carbons is going to be based off of pentane. This will be pentanone. We do need to give the carbon-oxygen double bond a number in this case because it definitely is 5 or more. And you can probably just visually see that if you go right to left here, that is going to give that sort of carbon-oxygen double bond the smaller number, and that would be 2-pentanone. And because we locked in the numbering that way, that means my methyl group will end up at carbon number 4 here, and that's going to be a 4-methyl 2-pentanone. Questions on that one there? All right, lastly here to draw, we're going to go backwards. So we see ONE, which tells us it's a ketone. We also see hexane, which tells us it's 6 carbons. So we'll start with that. We're just going to do 6 carbons here. 4, 5, and 6. The 2 and the ONE tells us that the ketone or the carbonyl group is at carbon number 2. Once again, since you're drawing it, you could either go left to right or right to left. I'm going to go left to right, which means my number 2 carbon would be right there. So again, obviously, if you went the other way, yours would be second in from the right there. That takes care of that. Because I locked this into place as this being carbon 1 and carbon 2, that would mean 3, 4, 5, and 6. So at carbon number 4, we have a methyl group, which is our 1 carbon group. And at carbon number 3, we have a bromine, right, which is our Br group. And now we're just going to kind of fill in some hydrogens. Again, the goal here is to get carbon to 4. We'll go with 3 there. We'll go with 2 there. 1 there. 1 there. None here as it has a double bond on top, which gives it 4. And here, 3. Any questions on that there? Again, if you're going to line structure it up, you do the same thing. 1, 2, 3, 4, 5, 6 carbons. Again, you could put your double bonded oxygen at carbon number 2. That would then make this carbon number 3 where the bromine would be, and that carbon number 4 where the methyl group would be, and you would have your line structure there. Any questions on aldehydes, ketones, naming, drawing, or any of those things?